Good morning, ma'am. So this is my fifth chosen topic in the inverse of a matrix. So for this lesson, we have these following objectives. First, find the inverse of a matrix if it exists. Use properties of inverse matrices. Use an inverse matrix to solve a system of linear equations. So let's proceed to matrices and their inverses. Consider the real number equation ax is equal to b. To solve this equation for x, multiply both sides of the equation by a raised to negative 1, provided that a is not equal to 0. So we have here ax is equal to b. So multiplying both sides by a raised to negative 1, we have a raised to negative 1 times a times x is equal to a raised to negative 1 times b. So the multiplicative inverse of a is a raised to negative 1. So because a raised to negative 1 times a is equal to 1. This means this is the identity element for multiplication. So that's why here a raised to negative 1 times a is 1 times x is equal to a raised to negative 1 times b. So the remaining equation would be x is equal to a raised to negative 1b. So the definition of multiplicative inverse of matrix is similar. Now let's proceed to the definition of the inverse of a matrix. So an n by n matrix A is invertible or non-singular when there exists an n by n matrix B such that A times B is equal to B times A is equal to I sub n, where I sub n is the identity matrix of order n. The matrix B is the multiplicative inverse of A. A matrix that does not have an inverse is a non-invertible matrix or singular. So theorem 2.7 states the uniqueness of an inverse matrix. Matrix A is an invertible matrix, then the inverse is unique. This means that the inverse of matrix A is denoted by A raised to negative 1. So example number 1, the inverse of a matrix. Show that B is the inverse of A, where A is equal to negative 1, 2, negative 1, 1. And matrix B is equal to 1, negative 2, 1, negative 1. So solution. Using the definition of the inverse matrix, show that B is the inverse of A by showing that A times B is equal to I is equal to B times A. So multiplying matrix A and matrix B is equal to 1, 0, 0, 1. Another, multiplying B times A, it will result to 1, 0, 0, 1. So the next example shows how to use system of equations to find the inverse of a matrix. So here is the example number 2, finding the inverse of a matrix. So find the inverse of matrix A is equal to 1, 4, negative 1, negative 3. So to find the inverse of A, solve the matrix equation A times X is equal to I for x. So here we have matrix A, 1, 4, -1, -3. We'll multiply by x. So we have x sub 1, 1, x sub 1, 2, x sub 2, 1, and x sub 2, 2 is equal to the identity matrix 1, 0, 0, 1. So multiplying this one, we'll have first row, first column. So 1 times x11, we have x11 plus 4 times x21, we have 4x21. Next, first row, second column, we have 1 times x sub 1, 2. So we have x sub 1, 2. Next, 4 times x sub 2, 2. So we have 4x sub 2, 2. Next is second row, first column. So we have -1 times x sub 1, 1. We have negative x sub 1, 1. Next, -3 times x sub 2, 1. We have negative 3x sub 2, 1. Next is second row, second column. So we have -1 times x sub 1, 2. We have negative x sub 1, 2. And next, -3. -3 times x sub 2, 2. We have -3x sub 2, 2. And we need to equate this one into our identity matrix 1, 0, 0, 1. So equating the corresponding entries, you obtain two systems of linear equations. So we have x sub 1, 1 plus 4x sub 2, 1 is equal to 1. Another, we have negative x sub 1, 1 minus 3x sub 2, 1 is equal to 0. Another, we have here x sub 1, 2 plus 4x sub 2, 2 is equal to 0. Another, we have negative x sub 1, 2 minus 3x sub 2, 2 is equal to 0. So solving this first system, you will find that x sub 1, 1 is equal to -3 and x sub 2, 1 is equal to 1. Similarly, solving the second system, you'll find that x sub 1, 2 is equal to -4 and x sub 2, 2 is equal to 1. So the inverse of x is equal to a raised to -1, or the inverse of a is equal to -3, -4, 1, 1. So generalizing the method used to solve example number 2 provides a convenient method for finding an inverse. Note that the two systems of linear equations, which is this one, x sub 1, 1 plus 4x sub 2, 1 is equal to 1, negative x1, 1 minus 3x2, 1 is equal to 0, and x sub 1, 2 plus 4x sub 2, 2 is equal to 0, and negative x sub 1, 2 minus 3x sub 2, 2 is equal to 1. So, to have the same coefficient matrix, rather than to solve the two systems of equations represented by 1, 4, 1, negative 1, negative 3, 0, and 1, 4, 0, negative 1, negative 3, negative 1. So all we need to do is to get the coefficients of the systems in the earlier example. So separately, to solve them simultaneously by adjoining the identity matrix to the coefficient matrix to obtain, so we need to join the identity matrix and matrix A. So we have 1, 4, 1, 0, negative 1, negative 3, 0, and 1. So applying Gauss-Jordan elimination to this matrix, solve both systems with a single elimination process as shown below or in the next slide. So we have here 1, 4, 1, 0, 0, 0, 1, 1. So what we did is to add row 2 to row 1 to produce new row 2. That is why became 1, 4, 1, 0, 0, 1, 1, 1. Then we need to multiply um, negative 4 to row 2 and add to row 1 to produce the new row 1 so that we can eliminate this 4. So the resulting matrix will be 1, 0, negative 3, negative 4, 0, 1, 1, 1. Okay, so applying Gauss-Jordan elimination to the doubly augmented matrix A and I, you will obtain the matrix I and A raised to 1, which is illustrated here. So we have 1, 4 from 1, 4, 1, 0, negative 1, negative 3, 0, and 1, 2, 0, 1, 1, 0, negative 3, negative 4, 0, 1, 1, 1. So this procedure or algorithm works for arbitrary n by n matrix. If A cannot be a row reduced, if A cannot be row reduced to I sub n, then I is non-invertible or singular. So finding the inverse of a matrix by Gauss-Jordan elimination, let A be a square matrix of order n. First, we have to write n times 2n matrix that consists of A on the left and the n by n matrix I on the right to obtain A and I. This process is called adjoining matrix I to matrix A. So we need to adjoin matrix I and matrix A. If possible, row reduce A to I using elementary row operations on the entire matrix A and I. The result will be matrix I and A raised to 1 or the inverse of A. If it is not possible, then A is not invertible or it is singular. So we could check by multiplying that A times the inverse of A is equal to I and I is equal to inverse of A times I. So for example, finding the inverse of matrix. Find the inverse of matrix A is equal to 1, negative 1, 0, 1, 0, negative 1, negative 6, 2, and 3. So begin by adjoining the identity to A to form matrix A and I. So adjoining the two matrix will have 1, negative 1, 0, 1, 0, 0, 1, 0, negative 1, 0, 1, 0, negative 6, 2, 3, 0, 0, 1. Use the row operations to obtain the form I A raised to negative 1 or the inverse of A as shown below. So first, multiply negative 1 to row 1 and add to row 2 to produce new row 2. So it will result to 1, negative 1, 0, 1, 0, 0, 0, 1, negative 1, negative 1, 1, 0, negative 6, 2, 3, 0, 0, 1. Next step is we need to multiply 6 to row 1 and add to row 3 to produce new row 3 so that we can eliminate this negative 6. So the resulting matrix will be this one. So the new row 3 will be 0, negative 4, 3, 6, 0, and 1. Next step will be we need to multiply 4 to row 2, then add to row 3 to produce new row 3 so that we can eliminate this 4, negative 4 here. So the resulting matrix will be this one and the new row 3 will become 0, 0, negative 1, 2, 4, 1. Okay, so the next step will be we need to multiply negative 1 to row 3 to produce row the new row 3 so that this negative 1 will become positive. So the new row 3 will be 0, 0, 1, negative 2, negative 4, and negative 1. Next, we need to we need to add row 2 and row 3 to produce row 2 so that this negative 1 here will become 0 or will be eliminated. So the new row 2 will be 0, 1, 0, negative 3, negative 3, negative 1. The next step is we will add row 1 and row 2 to produce new row 1 in order for this negative 1 to be eliminated. So the new row 1 now will become 1, 0, 0, negative 2, negative 3, and negative 1. So as you can see, this is now the identity matrix or this is now the I. So the resulting or the final matrix is 1, 0, 0, negative 2, negative 3, negative 1, 0, 1, 0, negative 3, negative 3, negative 1, and 0, 0, 1, negative 2, negative 4, and negative 1. So therefore, the matrix A is invertible, and its inverse is A raised to negative 1 is equal to negative 2, negative 3, negative 1, negative 3, negative 3, negative 1, negative 2, negative 4, and negative 1. So the process shown in example number 3 applies to any n by n matrix A and will find the inverse of A. If it exists, then A has no inverse. The process will also tell you that. The next example applies the process of singular matrix, one that has no inverse. However, before we will proceed to the next example, so remember that we can check if the inverse will be if our inverse is correct by multiplying or following this one. A times the inverse of A is equal to I, and the inverse of A times A. Now let's proceed to example number 4. Show that the matrix has no inverse. So take for example A is equal to 1, 2, 0, 3, negative 1, 2, negative 2, 3, and negative 2. Solution. So first, again, we need to adjoin A and I. So 1, 2, 0, 1, 0, 0, 3, negative 1, 2, 0, 1, 0, negative 2, 3, negative 2, 0, 0, 1. So applying Gauss-Jordan elimination, we obtain 1, 2, 0, 1, 0, 0, 0, negative 7, 2, negative 3, 1, 0, 0, 0, 0, negative 1, 1, and 1. So note that a portion of matrix has a row of zeros. So it is not possible to rewrite this one. So this matrix is not possible to rewrite matrix AI in the form I raised to A raised to negative 1. So this means that matrix A has no inverse or is non-invertible, or this matrix is non-invertible or a singular matrix. So, using Gauss-Jordan elimination to find the inverse of matrix works well even as a computer technique. For matrices of 3 by 3 or greater, for instance, we have 2 by 2 matrices. However, you can use the formula for the inverse rather than Gauss-Jordan elimination. So if A is a 2 by 2 matrix, we can assign the elements of the matrix as A, B, C, D. Then, A is invertible if and only if A times D minus B times C is not equal to 0. Moreover, if A times D minus B times C is not equal to 0, then the inverses is A raised to negative 1 is equal to 1 all over A times D minus B C multiplied to D negative B negative C and A. Example number 5. Finding inverses of a 2 by 2 matrix. If possible, find the inverse of matrix A. A is equal to 3, negative 1, negative 2, 2. B is equal to 3, negative 1, negative 6, and 2. So solution for letter A. For a matrix A, apply the formula for the inverse of a 2 by 2 matrix to obtain A times D minus B times C is equal to, so this is now A, B, C, D. So, getting the values of A, that is 3, D is 2, minus B is negative 1, and C is negative 2. So simplifying, the answer will be 4. So this quantity is not 0. So A is invertible. So we have, or A, matrix A has an inverse. So from the inverse, by interchanging the entries on the main diagonal, changing the signs of other two entries, and multiply by the scalar 1/4 as shown below. So we have negative, or A raised to negative 1. So the inverse of 4 is 1/4. So multiplying this one to the matrix 2, 1, 2, and 3. So remember that we interchange the diagonal, the main diagonal, which is the 2 and 3, and we interchange the sign of the other diagonal. So from negative 1 to positive 1, from negative 2 to positive 2. So multiplying it by 1/4, it will become 1/2, 1/4, 1/2, and 3/4. So therefore, the inverse of this matrix 3, negative 1, negative 2, and 2 is 1/2, 1/4, 1/2, and 3/4. Okay, for matrix B, you have A times D minus B times C is equal to, so what is our A? We have 3. What is our D? We have 2 minus, what is our B? Negative 1. And what is our C? Negative 6. So 3 times 2 minus negative 1 times negative 6. So it will become positive 6. So 6 minus 6 is 0. So it means that B is non-invertible. So wala siyang inverse. Next, another property for inverse matrices. Okay, so if A is an invertible matrix, K is a positive integer, and C is a non-zero scalar, then A raised to negative 1, A raised to K, C times A, and the transpose of A are invertible, and the statements below are true. So number 1, the inverse of A is equal to A. The inverse of A raised to K is equal to A raised to negative 1, A raised to negative 1, to A raised to negative 1 is equal to A raised to negative 1 times, or raised to K as the factors. For C, we have the inverse of C times A is equal to 1/C times A raised to negative 1. Number 4, the inverse of the transpose of A is equal to the transpose of the inverse of A. So in example number 6, the inverse of the square matrix. So compute A raised to negative 2 two different ways and show that the results are equal. The results are equal. So we have A is equal to 1, 1, 2, 4. So solution. One way to find A raised to negative 2 is to find A squared raised to negative 1 by squaring the matrix A to obtain A squared. So we have 3, 5, 10, and 18. And using the formula for the inverse of a 2 by 2 matrix to obtain a squared raised to negative 1 is equal to 1/4. So applying uh, the earlier method, we obtain 18, negative 5, negative 10, and 3 is equal to, so 1/4 times 18, that is 9 over 2. 1/4 times negative 5, that is negative 5 over 4. 1/4 times negative 10, that is negative 5 over 2. And 1/4 times 3, that is equal to 3 over 4. So another way to solve or to find a raised to negative 2 is to find a, or the inverse of a squared, by finding first the inverse of a. So the inverse of a is equal to, so 4, negative 1, negative 2, and positive 1. So multiplying this one to 1/2, so 1/2 times 4, that is 2. 1/2 times negative 1, that's negative 1/2. 1/2 times negative 2, that's negative 1. And 1/2 times 1 is 1/2. And then squaring this matrix to obtain, so we need to square both. The inverse need to square, so multiplying the matrix by itself, so we will obtain 9 over 2, negative 5 over 4, negative 5 over 2, and 3/4. Therefore, the previous answer or the previous matrix is just equal or produce a same result, which is this final matrix. So the next theorem gives a formula for computing the inverse of a product of two matrices. So theorem 2.9 states that, or for the inverse of a product. So it states that if A and B are invertible matrices of order n, then A times B is invertible, and the inverse of A times B is equal to the inverse of B times the inverse of A. Okay, example number 7. Finding the inverse of matrix product. So find the inverse of A times B for matrices. We have A and B. So A is equal to 1, 3, 3, 1, 4, 3, 1, 3, 4. And B, we have 1, 2, 3, 1, 3, 3, 2, 4, 3. So using the fact that the inverse of A and the inverse of B are matrix, the inverse of matrix A is 7, negative 3, negative 3, negative 1, 1, 0, negative 1, 0, and 1. Then the inverse of the inverse of matrix B is equal to 1, negative 2, 1, negative 1, 1, 0, 2/3, and negative 1/3. So by having this, or using theorem 2.9, it produces, we need to multiply the inverse of B and the inverse of A. So multiplying both inverse of the matrices A and B, so 1, negative 2, negative 1, negative 1, negative 1, positive 1, 0, 2/3, 0, and negative 1/3. And we have 7, negative 3, negative 3, negative 1, 1, 0, negative 1, 0, and 1. So applying the rule in multiplication of matrices, Okay, so we have first row and first row and first column. Next, first row and second column. First row and third column. Next is we have second row, first column, second row, second column, second row, third column, and the last one is um, third row, first column, third row, second column, third row, third column. So it will result to 8, -5, -2, -8, 4, 3, 5, -2, and -7/3. So one important property in the algebra of real number is the cancellation property. So that is if AC is equal to BC, if C or where C is not equal to 0, then A is equal to B. Invertible matrices have similar cancellation properties. So last one is we have systems of equation. So for square system of equation, those having the same number of equations are or as variables, you can use theorem below to determine whether the system has a unique solution. So theorem 2.11, system of equations with unique solutions. So if A is an invertible matrix, then the system of linear equation AX is equal to B has a unique solution. X is equal to the inverse of A times B. So we have here example number 8 applying the theorem or the systems of equation with unique solutions. So A, we have the system 2x plus 3y plus z is equal to -1, 3x plus 3y plus z is equal to 1, 2x plus 4y plus z is equal to -2. Letter B, 2x plus 3y plus z is equal to 4, 3x plus 3y plus z is equal to 8, 2x plus 4y plus z is equal to 5. And letter C, 2x plus 3y plus z is equal to 0, 3x plus 3y plus z is equal to 0, 2x plus 4y plus z is equal to 0. So here are the solutions for A, B, and C. First, note that the coefficient matrix for each system of A is 2, 3, 1, 3, 3, 1, 2, 4, 1. And using the Gauss-Jordan elimination, we will obtain the inverse of A, which is -1, 1, 0, -1, 0, 1, 6, -2, and -3. So for A, we have here, or the solution will be x is equal to 2, y is equal to -1, and z is equal to -2. For letter B, the solution will be x is equal to 4, y is equal to 1, and z is equal to -7. And for letter C, the solution is trivial, that x is equal to 0, y is equal to 0, and z is equal to 0. So I have here an activity 1 to 6. So all you need to do is to show that B is the inverse of A. So that would be the end of my presentation. Thank you so much for listening and have a great day.